Okay, I think we can kick off. Thanks everyone for joining us today. My name is Steve Sobel. I'm our global industry leader for media and entertainment at Databricks, joined by Brian Smith, our technical director for retail manufacturing. And we also have a few other folks that are on the line as well as we kick off our workshop on personalizing the omnichannel path to purchase with data and AI. Very excited that you could join us today. And before we get kicked off here, a few housekeeping items. Throughout this workshop, your connection will be muted. You can submit questions via the chat panel that you see as part of this interface here on Zoom. Questions will be answered at the end of our panel, as well as the end of the demo session. Feel free, though, if you have questions along the way, absolutely feel free to add them into the question panel. We can kind of take questions as they come in. We generally, when we do these workshops, we want them to be very collaborative. We like to get as many questions from our practitioners as possible. So don't be bashful, don't be shy. Definitely feel free to weigh in. And in case your colleagues miss this, or in case you're looking to get a replay, the session will be recorded and will be available for request after today's presentation. Before we get into the meat of the presentation today, I wanted to do a quick poll that you can see right now on your screen. We always like to get a little bit more granularity on who is part of our audience, kind of what they're interested in. That way, as we're diving in here, we can kind of specifically answer some of your questions. So you'll see the questions in front of you in terms of your role, what level within your organization, what type of organization you work for, where you are in your cloud journey, and a few other questions. Should take no longer than a minute to answer, but definitely will help us as we're diving in today. I will give everyone another 30 seconds to engage with our poll questions here. If you haven't filled out the poll yet, feel free to do so now before we close off here, and just again to get a better understanding of who's in our audience today. Okay, I think we've given everyone enough time. Let's see what answers we have for our polls here.
A few more just quickly trickling in. I'm gonna let them come in real fast.
Cool.
Like popping popcorn in a microwave, you just gotta wait for it to settle down.
Yeah. All right, I'm gonna close it now.
All right. So thank you for sharing your poll. Looks like we've got a big chunk of data scientists here, a few different data engineers, and a bunch of analysts. In terms of level, we've got a few managers, director, VP, and a lot of other. The types of organizations that you're from, looks like about a third of you are from retailers, traditional retailers or e-commerce, bunch that are not from the retail world. In terms of have you adopted the cloud for analytics and AI, big majority, 70% of you in the audience have said yes. And then next in is a few of you are planning to be migrating workloads over the next few months. What type of data are you using for advanced analytics and AI? Looks like everyone's using a little bit of everything: e-commerce sales, retail T-log, and loyalty. No clear winner in terms of a data set of choice there, but good to see the variety there. And what are the top data and analytics and AI challenges that you have? The number one answer here is data scientists, engineers, and analysts and business teams working in silos. This is something, of course, we see quite a bit of, and hopefully today we'll give you a little bit more kind of grounding in our point of view on kind of how we can help solve for these challenges, particularly when it comes to consumer engagement use cases, recommendation use cases, and the like. Last but not least, there was one other question. What are your top use cases for data analytics and AI? Looks like about a third of you said personalization. Another third of you said consumer segmentation. So this will be the content we're going to present today. Hopefully will be highly relevant for you, because segmentation, personalization are core parts of all things recommender systems. So we hopefully the content we have today will be super relevant. So thanks again for joining our poll there. To kick things off, our agenda today, we'll do a brief round of introductions. We'll talk a little bit about kind of the business imperatives behind personalization, what we're seeing in the market in terms of driving a personalized experience across the consumer lifecycle. We'll talk a little bit about why Databricks is differentiated to best serve personalization as a big data and AI platform. And then kind of the stars of the show, we'll be walking through a compendium of assets and notebooks that we have built that we'll make available after this call today to help you with all things personalization recommendation systems. One thing we're super excited about, we actually, the team that's joining us today have built out 11 different notebooks to help around these recommender system use cases. So we have a ton of assets to help you as you're looking to get started here. And again, throughout the session here, feel free to, in the chat panel, throw out any Q&A, any questions you may have, and we'll answer those as they come in, but also we'll save some time at the end of the presentation for conquering those questions. To kick things off again, my name's Steve Sobel. I'm our industry leader for communications, media, and entertainment. I spend most of my time talking with customers in this space, including those in the ad tech and martech space. So a lot of crossover with kind of retail use cases, but also the focus that we're seeing is around how do you optimize the direct to consumer lifecycle. So this is going to be this content is of course highly relevant for my industry. I know a lot of you are also from the retail industry, and we're thrilled to have my co-presenter today will be Brian Smith, who is our technical director for retail and consumer packaged goods. We're also joined today by 4 interns who, when I talk about these 11 notebooks that we have had built, these are the stars of the show who've really had the heavy lift here. This is a group of data science interns that have been with us for 3 months and have been, this is the work that we're going to show today is the fruit of their labor. So Yi Yan, Terry, Yi, and Balaji have been absolute stars, and we're really excited to kind of showcase the work that they've done with us over their time as interns with Databricks. Before we get started, for those of you who don't know us, we of course this whole workshop is being sponsored by Databricks. We are the big data and AI company that helps unify the worlds of data engineering, data science, and business analytics on one platform to help accelerate the pace of innovation that they have around their big data and their AI workloads. While we were founded by the 6 founders of Apache Spark, which is the open source big data processing engine that we see across many in the enterprise space, we also have been contributors to the top contributors to a number of other open source initiatives, namely Delta Lake, which is about making the modern data lake more performant, more reliable, and ML Flow, which is a data science tool to kind of help with more efficiency, more productivity around the ML lifecycle. We have the great fortune of working with customers all over the globe. We have 7,000 customers everywhere. We work with companies of all shapes and sizes across, financial services, retail, media, HLS, ultimately helping to solve big problems when it comes to the world of taking all of the data that you have, making it ready for AI and ML use cases, and doing it really fast. As I mentioned, kind of some of the customers that we work with, we're we're a platform. I always like to say, we provide the canvas, our customers paint the art. Some of the leading use cases that you see for some of the logos here today could be, in the manufacturing space. How do you leverage IoT to understand, your fleet, or understand any sort of distributed equipment, any sort of getting ahead of any sort of equipment failure. In my world of media, we work with customers like Riot Games that are doing near real-time or real-time personalization to help keep their platform sticky. We look at kind of the retail space where we're doing quite a lot around supply chain optimization, or the financial services space where we're specifically focused on risk management and understanding, detecting fraud at scale. No matter what the problem is, a big data problem, we help teams move a lot faster around helping to solve these problems, but also the ability to infuse AI and machine learning into the workflow is a key differentiator for us as a platform. Of course, today we're here to talk about all things consumer engagement and personalization. And, we live in this world now where kind of consumers have become more fickle than ever before. It used to be that you could throw an experience, you could throw a product, you could throw content at a consumer and it would stick or it wouldn't. Consumers now have more choice than ever before. And when we think about specifically in the retail world, we see this emergence, and frankly, the pandemic has just brought the future forward faster in terms of the amount of innovation that's going on and kind of the growth of direct-to-consumer services. We saw, in the spring, kind of the amount of innovation going on, the amount of growth in these e-commerce platforms growing in 10 weeks, what it took 10 years previously for e-commerce as a channel to grow. So we're seeing, more and more 2020 be the benchmark for, everyone doubling down on consumer engagement. And we're seeing also this, rapid growth in direct-to-consumer brands. In the retail space, we see, kind of the brands like Dollar Shave Club, Butcher Box, kind of, more specialized around consumer product needs really emerge. But certainly in the media space, we've seen kind of the whole industry pivot from wholesale to retail in terms of being able to build and scale direct-to-consumer services. But that's not to say retailers are missing out on this as well. We, of course, just recently saw Walmart Plus launch. We, of course, see what's going on with Amazon Plus. More and more we're kind of seeing direct-to-consumer as a channel. And, this kind of growth in direct-to-consumer is generating a wealth of knowledge, a wealth of data, and a wealth of understanding on what consumers are doing on your platform, how to provide a differentiated experience with them over time. But the challenges that we've seen in kind of the hyper growth that we've seen over this past year in e-commerce and kind of the direct-to-consumer channel haven't changed our intentions in terms of how do we drive a more relevant, a more personalized experience with our end consumers. It's really, this year hasn't changed much, but it's put more of a focus on important areas. When you think about, kind of the going back to, retailers 50 years ago, retailers knew who their end consumers were. You see here a butcher, a neighborhood butcher knows, who the end consumer is, what you like, how do we kind of create a personalized service with you over time. But now, as kind of, we kind of have the brick and mortar example in retail, but now we have these e-commerce players that are looking to scale these solutions over time. How do we take more distributed models to kind of create the same experience of intimate personalization where you're known, your likes are known, your behavior is known, and really start to translate these one-to-one old school experience into the new world of experiences that are driven by data. And while some people think recommendations, are, we go back to that example of kind of the old school butcher shop of, recommendation being about what product you will like or powering engagement, ultimately, when we think about recommendations, it's really about how do you differentiate yourself across the full consumer life cycle. Oftentimes recommendation systems or personalization, like you're thinking of it as a top of funnel, but really every single piece of kind of a touch point with the customer should be influenced by personalization, by recommendation systems. Specifically walking through kind of the typical funnel of what you see from a typical consumer life cycle. Of course, we always start with awareness. And, in the awareness of phase one, the most effective means for personalization is often through email. If 100 people enter the top of your sales funnel, only 3%, may make a purchase. This is kind of based on typical data that we see in kind of the kind of consumer trend space. Personalizing email is a great way to engage a customer at an awareness level. And frankly, we see this being a kind of key gateway for consumers as they're kind of onboarding in terms of how do you drive relevance off the bat? How do you kind of get a user that might be coming from a cold start, taking any sort of inclination you have on consumer preference to start informing that personalized journey? We have tons of statistics on kind of where personalization can feed in from a user cold start perspective. Salesforce had a study where they said 52% of consumers, if they don't see a personalized engagement right off the bat, they will leave your platform. People don't want generic messaging. They want to be known. They want to be spoken to in the time and context of their choosing. Moving on to the consideration phase, this is a key kind of milestone and benchmark for continuing to drive the personalized experience, whether it is how you create a personalized in-app authenticated experience. How do you create more personalization from a search perspective? How are you doing next best action, next best offer, personalizing your promotions, the ability to drive up and cross-sell? These are absolutely key components of and key intervention points that you can continue to drive recommendation and personalization over time. And, once you've gotten the consumer to convert, kind of up and cross sell, huge area where we see, people that are kind of focusing on kind of these recommendation systems. Once you get into conversion, this is where, maybe you have abandoned items that were put in a shopping cart, or maybe you have behavior showing intent that someone is likely to purchase. Maybe it is something like, we understand you've purchased these items in the past. Similar users are purchasing XYZ. Lots of intervention points here once you've actually gotten a consumer to convert. Once you've gotten through conversion into fulfillment, this is where you can leverage kind of personalized receipt offers, and this is where, really kind of a thinking about every touch point of the life cycle and where you can have an intervention is absolutely key to driving many of these use cases. And then, certainly last but not least, retention and loyalty programs for retailers. This is a huge area of focus. And again, as we're looking at kind of patterns of what similar buyers have used, what have purchased, things like cohort analysis, segmentation, again, being able to execute, personalization from an omnichannel perspective when it comes to retaining and kind of driving customer loyalty, improving NPS and CSAT, huge areas of focus for everyone that's in the direct-to-consumer space. So when we think about kind of how this works from a life cycle perspective, there's also the kind of behavioral aspect to this too. Personalization really only works when you're fully understanding, a full view of the customer, this whole kind of paradigm shift of getting to a customer 360, so you can start to understand behavior, intent, and kind of model behavior to drive more effective personalization over time. In this quick example of how behavioral recommendations work, we find that we have 3 customers that all purchase the same 3 products here, pink, red, and gray. Looking at the characteristics here of one of the consumers here, we see that they have little in common from a demographic perspective. So we have Maria here. She she's in Chicago. She's a little bit of a kind of mid-income relative to Ben and Sally, who are in different parts of the country. We see though that all 3, Maria, Ben, and Sally, they all like the same product. So, what does this tell us? I mean, this tells us that, we really need to get to a level of consumer understanding, behavior, intent to really start to differentiate ourselves and get to these one-to-one relationships with all 3 of these end consumers. The old way of doing things, it was all about, maybe we make assumptions based on demographic profile of what we think they will like. But when we're taking in clickstream data, when we're taking in preference center, when we're taking in augmenting with our data sets with third-party data, we start to kind of uncover and understand what are going to be regardless of what the profile is and what we're targeting, what actually is going to get the consumer to do something and drive them towards a purchase. This is a super simplified version of what recommending systems do. But essentially, again, it's kind of how do we model out and kind of take everything we know to create a one-to-one experience and ultimately drive towards a product conversion over time. So, we've kind of covered a lot in a short amount of time of kind of, the where recommendation fits, both from a life cycle perspective, but also from a perspective of, where behavior kind of an understanding behavior gets us to in terms of informing what goes into a recommendation system. But at the end of the day, recommendation engines do a few different things. Of course, the number one and foremost, they remind us of things that we like and or services that we might want to use again. So things like, think about, recommendation systems for, abandoned shopping cart use cases, or, hey, if you're on Netflix, you haven't finished this series that you may want to. How do we kind of increase time on site, ultimately leading to a conversion? When we get a conversion, upsell is going to be a critical area where retailers, direct-to-consumer players that are looking to increase average shopping cart size, increase their customer lifetime value. Upsell is a key means for kind of taking what we know about a end consumer and driving a recommendation that will get them to convert. Cross-sell, another area. So if you like X, you might like Y. Another area where recommendations come in. We, of course, Amazon, there's no one better on the planet than doing this, but We're seeing retailers of all shapes and sizes that are trying to get to cross-sell, ultimately, again, with the goal of increasing average shopping cart size, increasing customer lifetime value. And last but not least, recommendation engines are, intent is to introduce. So new things that you may like based on past behavior, past shopping. So again, we share this to say there are different kind of ways and different kind of moments in the life cycle where recommendations are going to be relevant. But, the challenge oftentimes that customers have is the flexibility that they have in terms of bringing all of the data that they have, whether it is streaming data, batch data, POS data, ERP data, whatever the data set is, challenged by the scale of the data, the complexity of being able to get to real-time or near real-time use cases, particularly when it involves the ability to handle streaming data coming in. And what we see is, more and more customers that are building out their personalization and recommendation systems on Databricks for our ability to, again, handle all of your data, be able to make it ready for ML use cases, and do it really, really fast. So if we think about some of our largest customers as a company, kind of all things personalization, all things lifecycle experience, these are all critical areas where our customers are investing, and really to kind of bring this to bear and kind of, again, why do this on Databricks and kind of why we're here today. We're going to show you some of the assets that we've made available to actually get to this world where you can quickly spin up a POC or do tuning around a personalization use case that you have now. Ultimately, our goal here and what we're going to show you through this workshop today is the toolkit that we have available to move more rapidly around these personalization use cases. For those of you who don't know and kind of how this all comes together on our platform, I know I'd kind of mentioned the concept of we have the ability to take all of your data, make it ready for AI and ML, and do it really fast, ultimately with the objective of getting to business use cases. I won't spend a ton of time on this slide, but essentially think of us as an abstraction layer within your infrastructure environment. We are a first-party service on Azure. We are a preferred service on AWS. We sit as an abstraction layer on top of your either S3 or blob storage. We make it such that as a unified data service, we can kind of take batch and streaming. We can take structured, unstructured, raw data, image data, voice data, be able to kind of take it such that you have a processing engine that can either get to better and faster ML use cases or better and faster BI use cases. So we have a data science workspace that's all around, how do we have one platform for data engineers, data scientists to be able to work from, ultimately with the goal of driving innovation faster. And we also work with a number of BI partners, Tableau, ClickLooker, Power BI, and others, where if you have a BI use case, we want to be that real-time processing engine to get you data results faster and faster. Before I turn over to my technical counterparts here, when I'd kind of mentioned, some of the challenges that we kind of see in the space around all things recommendation, and there's kind of two big ones, and I'm going to turn it over to Brian Smith in a moment, our technical director for retail and CPG, who's going to talk a little bit more about the challenges that we see around design flexibility and scale. Design flexibility is, the ability to kind of make decisions that impact your ability to achieve your goals, and being able to kind of be flexible around model development. And what we see with all things personalization is it is just as much art as it is science. There's a lot of learning that goes on based on how you're executing, and in terms of the model performance and kind of the downstream challenges that you have with kind of operationalizing a lot of these models. But we also see a lot of challenges around scale. Be it, kind of the challenges I mentioned earlier on joining batch and streaming, being able to handle streaming full stop, and really kind of the ability to have a platform where you have flexibility and you can handle scale is a huge differentiator as you're thinking about personalization, and something that we're going to be covering off today. So with that, I will turn it over to Brian, who will be walking us through the assets that we've built around all things recommendation and personalization, and hopefully get you a little bit more information on how you can use some of these models and some of these notebooks assets in your own environment. So with that, Brian, I will hand it over to you.
All right, let's switch screens. Are you able to see my screen now?
Yes, sir.
All right. Hey, so thanks for the introduction. And yeah, I really want to handle those last 2 points that Steve was putting out there. When we started this journey about 3 months ago, I think we were a little naive in understanding just how diverse this whole space is. And so we made a conscious decision as we got into it that we really wanted to focus on understanding the fundamentals. As Steve mentioned, different legs of the customer journey require different strategies for recommendations because you have different goals and your customers have different goals. And so that means that along the way, when we're designing these things, you're going to see a lot of spots where we really have to think about what's the right approach to hit that goal, hit that metric, or whatever it is that we're after. And it allows you to bring a lot of creativity into how you design these. So we focused on fundamentals here. And hopefully this will help you if you're getting started on the same journey with, kind of figuring out where you're going to go. So I think as you go through here, you're going to see us wrestle with those things, certainly ask questions about other ways we could have tackled things inside of here. The other thing you're going to see is that we're going to spend a lot of time wrestling with scalability. Recommenders, and you'll start to understand why here very shortly, have this nasty habit of going exponential on us in terms of the complexity that we have to deal with, the number of computations. And so we are constantly thinking about what's the right way to tackle that. Because when we think about recommenders, we want to take our users' input into consideration. They are constantly engaging our website, our apps, our other services. We need to keep our recommendations fresh and current with what they're actually doing. So we can't let scale become a limitation. And while we like to talk about the scale that we can achieve with Databricks, the reality is there's a cost performance type consideration that we have to give here. We can achieve incredible scale, but do we really want to pay to do that if we're doing it in unsophisticated means? So you're going to see a lot of that in here. In terms of the notebooks, though, let me just give you a sense of what we're talking about. We typically, when we do these webinars, we have one or two notebooks that we highlight for folks. And as an FYI, and I see a question here in the chat regarding this, we will be making all these available to you. So everything you see here is built off public data sets. You can download this code, bring it to your environment, kick the tires, tweak it, and adjust it to your needs from there. But there's just a tremendous amount of content that we've put out here to support this. Anyway, just want to make sure that you have awareness of that. But let's jump into the first of these. This is our collaborative filter. Let me go ahead and get Balaji on the line, if you're ready to go, and let's jump into this. So Balaji, tell us a little bit about this type of recommender.
Hey, Brian, thank you. Excited to be here. So when we think of collaborative filtering, we are trying to give personalized recommendations to each customers. So think of a scenario such as customers like you also bought. So you would experience this in everyday shopping at an e-commerce website, right?
Yeah, so I'm thinking like if I'm a retailer and I've got a site or an app, I want to help you find the products you want, but I want to suggest other things that I think that you might be interested in to maybe expand the shopping cart or to assist you in getting the maximum value out of those products. So yeah, I think we're all familiar with this type of recommender. So let's take a look at the data set real quick that we use for this. Can you tell us about the Instacart data set a little?
So we have used the Instacart dataset. This consists of over 3 million orders placed by around 200,000 users across 50K products. So although this will not be a huge volume of data, but it is really big enough to be applied in a real world scenario.
Yeah, this is one thing when we're setting this up. We try to find ourselves what we thought was a realistic data set of a reasonable size. 200,000 users, 50,000 products in here, 3 million transactions. This is pretty sizable, but certainly we deal with bigger stuff. That said, we were a little surprised how quickly the number of computations can get out of hand, even with a data set of this size. So I think people are going to get a lot of mileage out of seeing what we've had to do to achieve scale with this. But if I'm looking at the data structures that we have here, I see orders, I see products, a little bit more information about the products. I don't see ratings. And when I think about recommenders, I'm usually looking for some sort of a rating, 3 stars, 5 stars. Where's that data here?
Yeah. So as I said, in collaborative filtering, we are giving personalized recommendation for each user. So in order to do that, we need interaction data of the user with the products. So explicit ratings will be good, such as if you buy a product and the e-commerce website asks you to rate any stars out of 5 stars usually. So in a retail shopping scenario, nobody will do it actually. So there'll be very few who will rate like 3 or 4 stars out of 5 stars for a 3 lb onion bag, right? So to remove that hurdle, we are going to use the purchase frequencies as our ratings. So this concept is called implicit ratings.
Okay, so yeah, I mean, I don't ever go on when I shop online for groceries. I don't give like 5 stars to a set of bananas, right? That just doesn't make a lot of sense. So it looks like here you're getting creative in terms of how you do this. You're using the past purchase patterns. If I was doing this in another context, I might take a look at maybe someone's browsing my site. You know, what pages are they clicking on frequently? I might take a look at dwell time. There's any number of ways we can get at implied ratings. But I'm thinking there's a bit of a challenge with this that I need to consider. You know, in this scenario, I mean, think about it. Maybe I've been shopping with this website for 3 to 5 years. And so I'm going to have a much longer purchase history and the ability to accumulate more purchases than you, Balaji, who just joined maybe last month. So how are you dealing with that?
Yeah, if we take that scenario, we'll have a scaling problem. So we have to fairly compare each customer with the other customers. So to remove that hurdle, we are going to standardize this range. We are going to use L2 normalization for the standardization. You can read the justification of the need for L2 normalization in the notebook.
Yeah, and guys, just for the folks online, when we were going through the literature, we see a lot of places where people are normalizing things, but it's kind of taken for granted, I think, for why we're doing that, why that's needed. And so we did spend a lot of time in here hitting on this because it was something where we felt like we were just kind of repeating things that other people were doing, but weren't fully understanding it. So we've put a lot of energy into that here. So hopefully you can kind of come to that same level of awareness that took us quite a time to come to help you with your stuff. But let's get on to the actual recommenders. So again, remind us where we are with this type of recommendation and how these recommenders work.
Yeah. So anyways, we keep that in mind. We'll come to our goal now. So we are trying to give recommendations based on the customers like you also bought. So there are two approaches that this scenario can be implemented. One is user-to-user collaborative filtering and item-to-item collaborative filtering. Now I'm going to talk about the user-to-user collaborative filtering. In this in this filtering recommendation technique, a user will be compared with every other user, and we would find the similar users and give the recommendations based on the similar users' products. So if you see the figure, you can see that user A and user B are compared. And they have very much similar patterns because they have purchased similar items. So in this case, user A will be recommended users B product.
Okay, so I'm going to look around for different users that are similar to me. And if the more similar we are, if you like something like you like radishes, and I've never bought radishes, that could become the basis for a recommendation here. But Balaji, I'm looking at this, I'm a little bit concerned. You know, you've got, we said 200,000, it's like 206 and some odd users here, and hopefully that's going to be something increasing over time. If I have to go and compare every user to every user, you're talking 40 billion different comparisons. So this is a really small data set, but already I'm a little concerned about that. And I can think about it, right? User A to user B is the same as user B to user A. Maybe I can cut this in about half, but still 20 billion comparisons is, you know, I don't know if I really want to go down that path. The other thing I'm looking at here is causing me a little concern. Let's see if we can scroll down and take a look at it. Is that when I do these comparisons, I have to take a look at what you purchase across all 50,000 of these different products. Now, not everybody buys all those things, so we have some tricks to kind of deal with some stuff, but still you're talking about a lot of calculation work with each comparison. So how are you shortcutting this? Because I just don't see this as sustainable doing a kind of a brute force attack.
Yeah, I mean, this approach really takes a toll on the infrastructure and the computation time. But I really got you covered with a powerful technique called LSH, which is locality sensitive hashing. We are going to use this fast approach to divide users into buckets that are likely to be similar. So what I'm really going to do is that the LSH works by shooting hyperplanes randomly and place users in buckets based on whether they are above or below the hyperplanes. If you are in the same bucket, then you are statistically more likely to be similar to the users in the same bucket.
Okay, but I'm looking at this top one here, right? I mean, hyperplane, you know, maybe that concept doesn't make sense, but I'm looking at this line that you shot here between these folks, right? I've got A and B are above the line. I've got C, D, G that are, you know, below it in this first one. But I'm looking at B and C aren't that far apart in this space. And because you randomly shot a line there, I'm not going to look and compare B to C. So how are we going to overcome this problem?
Yeah, that's really a good question. So I'm going to do this iteration for a few times and find the match of users in different buckets across different iterations. So by doing this, I'm reducing the impact of randomly shooting hyperplanes, but still, this is just an approximation, but it is really fast.
All right, so if I get this straight, right, we're going to randomly select these things. We're going to put people into buckets, and we're going to assume that people in the same buckets are more likely to be similar to each other than folks outside the buckets. Because it's random, the way we're going to deal with this is we're going to do this a few different times. We're showing 3 here. We might do more, we might do less. But if anywhere in there you're in the same bucket, we'll give you consideration. So I notice here that A and B, or sorry, B and C fall into the same buckets inside the blue table. And so at some point, I will have the opportunity to compare B and C. Okay, but it's still an approximation, right? And guys, this is actually a really powerful technique. I don't know if you noticed how much code I had to scroll through. We have taken time inside this notebook to do a detailed breakdown of exactly how this works, compare it to brute force calculations on a limited subset so you can exactly see what you're getting and understand how to tune it for your needs. So I would encourage you, if you've never heard about LSH, this stuff works really fast. It is amazingly good at dividing stuff up here. It's a great technique. I think is underutilized. I would encourage you to take a look at it. But that said, let's get over to the actual recommendations. So help get us reoriented to this. We've been talking a lot about hyperplanes. So what again are we trying to do here?
Yeah, back to our basics. The goal is to find similar users based on the purchases that they made and give recommendations. So the scenario is customers like you also bought. So we have used LSH to achieve that, and we have found the similar users for each users, and we are going to compute recommendations for all these users.
Okay, so we've gone ahead and put everybody into their buckets using LSH. And now we're doing the comparison. So talk to me about a couple strategies that we could use for finding similar users with inside those buckets.
Yeah, you can actually use two strategies in this finding the similar users. One strategy is that you can find the n number of similar items. Like if you want to find the top 5 similar users for a particular user, you can do in that approach. And the another approach is that since we are doing an LSH, the LSH calculates the similarity based on the distances, Euclidean distance, for example, you can say. So you specify a certain range and then retrieve all of the users from this range. So these are the two approaches that you can practice.
Right, and so when we were going through this, we made the decision that we wanted to base similarity based on the concept of Euclidean distance. So how far apart inside this space these different users are. You could certainly use things like cosine similarity or Pearson's correlation or any number of different distance or similarity metrics inside of here. To be honest, we kind of lazily went with Euclidean distance because it was available to us out of the box with LSH. But I think you'll see as you go through some of the code how you could easily implement your own distance calculations using some simple techniques in here. But okay, so we have distance, but distance between people isn't similarity. We said the whole thing's based on similarity. So talk to us about how we get to similarities.
Yeah, when you say distance, it is somewhat different with the similarity. So we have calculated the similarity for each user with their similar users based on this calculation. And you can see in the notebook that we have calculated the similar users in Excel.
Okay. And so it looks like too, when we think about the similarity, that little formula we had there, it's a very simple conversion. It does need to be rescaled though to get everybody kind of into a 0 to 1 type range that we're normally accustomed to. So you've got some logic here for that. And there we go. We've got a sample user here. We throughout these notebooks, we're going to beat up on this user 148. And we're looking here then at the other users that are similar to him or her. And you can see that presented in terms of distance, but also in terms of similarity and the rescaled min-max similarity here. All right, so we've got ourselves our similarities. Here we are calculating this stuff. How are we converting this to a rating though?
Yeah. So now we are really targeting the calculation of a recommendation score. So similarity score will be used as a weighted average, weighted average of product ratings. So the recommendation score will be calculated by averaging the similarity weighted ratings from similar users.
Okay, so if you and I are similar, I look at the degree of similarity between us. I look at your implied rating of a particular product, and I take in consideration the degree of similarity to then convert that into a rating for me. And then, yeah, this is just weighted averages. So really fairly straightforward to calculate. Let's take a look then at evaluations on this. Now, when we got to the evaluation part of this, we found this really great article that we put a link to in here that talks about the different ways to think about evaluations. We saw over and over that people were doing mean squared error or root mean squared error for this. And that really works well when you're talking about trying to predict the actual rating scores that people give you on kind of fixed scales, but doesn't really work well here. So we actually pivoted and went to a different approach on this. It's highlighted in a fairly popular paper. It was put out by a group doing media related stuff with AT&T. But fundamentally, it gets at the problem of that we're going to use these ratings to basically create these sorted lists and create ranks. I'm going to skip down here. There's a lot that goes into this. But we'll see if we can't kind of summarize how we're tackling this. What we do here, if we think about the ratings that we're calculating, these weighted averages that we're calculating, there are means to sort things from kind of the most likely to be of importance to the least likely. If we calculate a percent rank on that, then our most likely product is going to have a 0.00 score assigned to it, and our least likely product is going to have a 1.0. What we can do is if we hold out some information from our calculations, we look at your future purchases relative to past purchases, we'll make we'll calculate these recommendations based on your past purchases, and then look at where you hit on average in that percent ranking scale. When we do this, if we see you're coming in around 50%, then really what that's telling us is that we're just kind of randomly throwing things at you. And on average, you're kind of picking something kind of in the middle of the sort order. The higher we can push you towards the top, and of course, that's the lower the number that we have here, the more it is that we're honing in on your particular interests and showing you things that are relevant. So you can think about this as the number goes down, there's less garbage for you to filter through to get to what you really want. So Balaji, let's take a look at what we actually got in terms of the score here. Blow this up for folks. So this is pretty good. I mean, why do you think this is? This is a 0.3%. Why do you think we got this kind of rating here?
I think we have really used all the novel products as a recommendations. So we might not be overwhelmed with the popular products.
Okay, so what we've done here, right, is we've looked at you similar to other people. We've used that as the basis for recommendations. When we saw this score initially, honestly, we were a little surprised at what we got here. But when we took a step back and we thought about this data set, it kind of makes sense. Think about how you shop at a grocery store, and that's what this data set is grocery purchases. You kind of buy the same things over and over. And so if you and I are similar because we kind of buy some of the same things, we're probably going to keep on buying some of the same things with minor variations on it. So in a grocery scenario, it would seem natural that we would have these high scores. Now, this is great if I'm trying to facilitate you getting through the purchasing process very quickly. I show you exactly what you want, click, 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 it goes in the shopping cart and you're out the door. But if I'm trying to introduce new things to you, I may actually want to rethink how I'm approaching this and actually look for lower scores so that I'm putting things in front of you that might be of interest, but I'm putting newer things you maybe haven't been exposed to before and kind of expanding the cart. Now, that said, we're kind of curious on this. How does this relate to just kind of a naive type model? And one of the really common naive recommenders that's out there is where we take a look at the most popular products. So we just looked across the board at all the folks inside of Instacart and just said, look, use the popularity of a product as the means by which to create this ranking and redo the evaluation with that same holdout set. And here's what we came up with. So this is still better than just doing random stuff in front of people, but it's nowhere near as good as taking into consideration what people have actually historically bought. So in a lot of ways, our customers are telling us what they want to see, and we're taking advantage of that to show it to them versus just throwing things out there based on overall popularity. All right, so let's flip to a different type of these. And Yi, help us understand what we're looking at here.
Yeah, thank you, Brian. So remember when we build a user-based collaborative filtering, we just blindly compare two users across through 200,000 users, which result about 20 billion potential user comparisons. That's a huge computational cost. And also users' neighborhood can be changed frequently as more users come in and out. So how to scale and maintain the system becomes a big concern. So we gotta find a shortcut to limit unnecessary comparisons. We think that if we can only compare two users who have bought at least months of same products, we can see a path to reduce the number of required comparisons. Like the enemy showed us, the user A and user B, they all bought the pumpkins. So that's why we only compared user A and user B.
Okay, so let me make sure I understand this. When we were doing Balaji's technique, we were looking at all users without any consideration if there's overlap. But the bottom line is you and I have no possibility of being similar unless we have at least purchased one item in common. So we're gonna take advantage of that. The other thing is I'm really not gonna be able to recommend other things to you unless I've bought something other than that one thing that we have in common. So what we can really do is we can take what Balaji was doing with the user-based collaborative filter, and we can kind of turn it inside out, starting with a look at product combinations, and then looking at what what they actually bought, and looking at the popularity of things in combination with their purchase history. So it's kind of an inversion of what we did there before. Now, I'm kind of curious though, what does this mean in terms of the number of computations I have to perform?
Yes, so with this shortcut in our mind, let's jump into the item-based collaborative filterings. So in the item-based collaborative filterings, we are going to compare the similarity between two items. Instead of just randomly select two items to compare, we only compare two items that have at least two common users that have bought them. So with this mechanism, we can see our comparison cost is only 56 millions compared to randomly selecting two items from 50,000 items where the comparison cost is going to be 1.25 billions. We achieve a tremendous computational cost saving.
Right, so instead of saying, hey, look, let's take 50,000 products and let's compare it to other 50,000 products and we'll come up with 125 billion unique combinations that we now need to go explore, we actually look at the combinations that are actually occurring in this data, and all of a sudden the number of comparisons we have to perform drops to 57 million, which is really manageable, especially with a system like we're running here. My concern though is when we were looking at what Balaji was doing before, he was comparing the users and he had to look at 50,000 products relative to the 50,000 products for the other user with each comparison. So while you've got the number of product comparisons down, I'm a little concerned that I now have to compare 200,000 users to 200,000 users with each one of those. And maybe that messes up our, the computational savings that we thought we were going to get from this.
The answer actually is not, we don't need to do that because the number of users associated with each comparison will be different, but each comparison will have the same number of users on the product A side as on the product B side. So this allows us to build a dense vector that's specific to each comparisons. So meanwhile, when we visualize the number of users associated with the product comparisons, we can see the most product combinations occur only between a very small number of users. So using the brute force could easily handle it.
Okay, so in the past we use LSH, we could use some other tricks to kind of pare this down. What you're seeing here though is I've got a manageable number of product comparisons, 57 million. And for each of those comparisons, the number of users that I need to consider with each comparison varies, but for the most part, it's a manageable number. And I am seeing there are some extremes here, right? I've got a couple of folks that are getting at about 30,000 some odd users have purchased some particular combination down here. But in those situations, we could do something like random sampling to keep it a more manageable number if we needed it. So, okay, this sounds like this might be a viable approach for us. So we go through here, and I'm going to skip over a bunch of code where we actually do all the calculations, but you can see we're getting at distance and similarity very similar to what we saw before, but we're doing product-to-product type comparisons. We're now coming into here, and we are building the actual recommendations. We're doing some of the same weighted averaging that we saw before, but with a different starting point, where I'm taking the users, each individual's users' product purchase history, using that to then go and look at the products that are found in combinations with those products, looking at the degrees of similarities and the ratings, calculating stuff, and then here we go. Now I've got a list. So let's see how this performs. So we come down here, we do all this, we do our calculation, our evaluation metric, and here's your result. Yi, this sucks. So what's going on here?
Yes, I know the performance is really horrible. It's even worse than you just randomly recommend a product to the users. The most likely reason is that we were not discriminating items. We were just saying if a pair of products has very high similarity score, we just recommended it. But it might that only one person has purchased these combinations. In other words, we were leveraging all the product combinations with no considerations of how many users may have actually purchased two products. Another reason may be even if we set up a number of common users, there will still a set of the combination will occur a lot, and we still take them into considerations. It will result in the recommendation. It will result in recommending so many products to users. So you can see when you go to the evaluation chart, when we add these two constraints, for example, first, if we limit those products we recommend until a product recommendation exceeds the minimum threshold in terms of the number of user rating, we can see our mean percentile ranking going down. That means our performance getting better. Like in our scenarios, the minimum threshold is a 6, has the best performance.
Okay, so let me make sure I understand this, because this is kind of an interesting notion. So before, when we first did our recommendations and we got that, I mean, not even random. It's like I'm purposely throwing things at you that I know you don't want type result before. We really weren't in any way filtering out kind of garbagey stuff. If I had someone who came in, this is the only time they ever shopped at my store, they bought 2 screwball things in combinations, right? All of a sudden, that combination has a high rating and it gets forced to the top. And so what we need to do here, it looks like, is set some minimal threshold. So guys, we got a lot of recommendations we could make, but we got to have at least this many customers who've actually bought those things in combination. For this data set, it looks like that sweet spot for most of these is somewhere between 5 or 6, which is not real high. What I think is interesting is if you start to elevate the minimum number a little bit more, you start to see that our evaluation metric starts to degrade. So remember for this one, right, the lower the better on this one. I can imagine too that it might vary based on product, and so we might want to be a little more flexible how we think about this, and that's part of the art of building these things. But here we're just going to do an across the board kind of cutoff on users. But then the other thing we're looking at is when I set the bar this kind of low, I still have a lot of product combinations that come in and meet that minimal requirement. And so what I'm looking at here on the different lines is saying, well, let's only take the top 2 most, or the top 3, or top 5 or 7 or 10 most of these. And let's use that as the basis for our recommendations. And when we do that, it looks like the more we take into consideration, again, the more junk we start putting in front of people, that for this data set, it helps to be a little more constrained. if we tie that back to what we saw before, I think this is very particular to a grocery scenario where, again, users tend to get into a bit of a rut in terms of what they buy. I know for me, there's certain staples that I go back to over and over again, and I don't deviate from that. But in a scenario like a fashion scenario, the shape of this curve may vary quite a bit. And it may be that I actually do want to show you quite a few more things to get the hits that we need here. So I think this is one where we really want to think carefully about our business scenario, our goals, and then let the data help steer us towards the right settings on this. And Yi, thanks for playing along when I said that it sucks. Of course, you know the outcome of where we're headed with this. This is great work, so thank you.
No problems, yeah.
All right, cool. So guys, we're gonna talk in one of the blogs, go into it deeper about how we actually take all this stuff and deploy it and operationalize it inside of our environment. But in the interest of time, I'm gonna jump to a different type of recommender. And Ian, maybe you can get us oriented to this. Tell us a little bit about this type of recommendation and when we might use it.
Yeah, sure. So imagine you are searching for a specific coaster that you saw at your friend's place last week. And you do know the exact name of that coaster, but you do know that it is used for beer and have a picture of a beer mug on it. Then you can start to search for those keywords. And then the content-based recommendation comes in by showing you different related items. Once the recommender helps you to find that coaster, it then can offer more similar choices for you to explore and make better choices. In the end, you bought that coaster and became happy. The retailer secured the transaction and made money, so everybody is happy.
Okay, so let's think about this scenario. And if you're not familiar with coasters, you know, my wife got onto me the other day. I put a beer glass onto the table, and she's claiming that I've ruined the table. We'll put a poll up to see who's right and wrong. You get to vote on that here towards the end. But I went out to a website and I'm looking for beer coasters, and I found something that's kind of there, but I'm scrolling around the page and I want some alternatives that might be similar. So I have something to look at, and I can kind of help me make better judgments about whether I want this product or if I want to steer to something else. So tell us a little bit about the data set that we're looking at here.
So we have two kinds of data. The first is metadata, which contains product-related information such as product titles, descriptions, and categories. Then we have the review data, which contains users' explicit rating from 1 to 5 stars and their reviews.
Okay, so this is the 2018 Amazon data set. The University of California at San Diego hosts this data set. We've got information here on how to download it. We will encourage you to go take a look at the terms and conditions on its use that are out there, and then pull it in appropriately. Yeah, when we get to the actual data set, just to point out to folks, there is a lot of content inside this data set, and we purposely decided that we want to focus in on just a few aspects of the product information. We're going to take a look at title, description, and category, but there's far more data inside these that you could use. The problem that we ran into was a lot of this data is fairly messy, and I think that's a consequence of how it was actually collected. And so we have to spend a lot of time inside this notebook cleaning up the data. So you're going to see a lot of tricks for deduplicating. We're going to do a lot of stuff with removing unescaped HTML and other HTML tag structures inside of here. There's a lot of work that gets to go to make this stuff a little bit more usable. Similar for reviews, we're going to constrain what we actually are going to use here, but there's far more information that you could pull in. So you just add the additional fields that will come into the data frame and we go from there. But this is the data set with which we're going to make these content-based recommendations. So Ian, talk to us a little bit about how we get started using something as simple as, say, like a product's title, the name that's presented there on the screen.
Mm-hmm. So as the image shows, we're trying to compare different products and find those that are similar. And right now we're just focusing on the content itself, separate from the user profile. And the challenge is, how can I get those kind of features when I only have words? So our product have titles. So can we just use title to determine similarities for now? And we need to convert the words into numeric representations for the computer.
Okay, so I'm looking at this, right? Here are the titles for some of these products. We have about 11.5 million of these. So there's actually quite a few products that we're dealing with here. I think that you and I could sit down, and we probably could do 11.5 million, but you and I could sit down and take a look at these titles and come up with some sort of assessment of, kind of how similar they are. But you're right, if we're going to turn this to a computer, I've got to figure out how to turn these words inside these titles into something numerical the computer can understand. So talk to me about the steps you're taking here.
So we implement a technique to quantify the importance of words in titles called TF-IDF. But we first need to do some prep work on the text. So we first break down the titles and split the titles into bags of individual words.
Okay, and then from there, where do you go?
So as you can see, the bags of words contain some chunks like stop words such as the, and, or, which have no meaning. And it also have words that have the same meaning, but in different forms, such as the verb see and saw. So we standardize these words using lemmatization, which basically turn them into their dictionary root.
Okay, so you're using lemmatization. Talk to me about that versus stemming, because I see stemming occurring quite a bit in this space.
Yeah, so stemming simply get rid of the word suffix. It chops the tails of words. So for see and saw, it will return the letter S. And lemmatization, on the other hand, take language morphology into consideration. So see and saw will return as the verb see.
Okay, so if we're doing lemmatization, it's a little bit smarter. It has an understanding of the language that we're looking at. It's looking at things like parts of speech, and it's trying to standardize with a little bit more knowledge there. We use NLTK for this, and just as an FYI, NLTK is pre-installed on the Databricks machine learning runtimes in the current versions of that. But what is needed to make this work is you do have to download content that's been tagged and prepared for use by NLTK, something that's called a corpus. We used WordNet for this, but that has to be installed separately. So at the top of this script, and anywhere where we use NLTK in this manner, you're going to see what's called an initialization script. And we'll auto-generate that for you. You'll need to tag that to the cluster, and that'll install all the remaining components that are needed onto the worker nodes, but all that's at the very top of this notebook and subsequent ones where we use this. And so there's quite a bit of code that goes into this. I see you've got it packaged as a pandas UDF that we can apply to our data frame. I'm then looking over here at your lemmata. And if I go through here, yeah, I see the junk words are gone, or the stop words if we're being a little bit more correct. And I see certain things have been kind of cleaned up in reasonably appropriate manners as we go through there. So how do I take this and then turn it into these numerical scores that you were talking about?
Yeah, so once our words are ready to go, we counted how many times they appear within a title. Since our titles are relatively short and most words don't occur more than once, so we limited the counting to the top most occurring words. And this is our TF score.
Okay, so TF inside of TF-IDF stands for term frequency. You're just counting the number of times a word occurs in a given title. Most of the time, that's going to be 1. Occasionally, we have seen some 2s and 3s pop up in there, but usually 1. But to make sure we're not just counting everything, we do limit it to the top most frequently occurring words across the data set that we have. We are using the count vectorizer here, which is actually doing an explicit count where every one of these words kind of is given its own spot inside of a vector, and the count's being done with 100% accuracy. We're going to come back to this notion here in just a little bit, but just kind of keep that in mind. But that's the TF part of your TF-IDF. What about the IDF part?
So the IDF part, we counted how many times they appear across all the titles, because words appear too often across all titles carry less important information. For example, if the word design appear in all the titles, then the word itself means nothing for a later comparison. And the IDF score is finalizing these words. And combining these two, we have our final TF-IDF score.
Okay, so we're counting the number of occurrences to understand how significant it is inside that title, but we're also looking across all the titles, and we're saying if this word's overused, it stops carrying as much meaning, and we're using that to then calculate scores for these different words, and we can see those over here on this data set. Cool, so I now have these numerical values. Now, one thing to point out is a lot of libraries that are out there that do TF-IDF calculations will return the data pre-normalized. These libraries here, which do it in a distributed manner across the Spark cluster for us, they do not. So we have tacked on a normalization step so that we can then produce accurate similarity scores. So I tell you what, let's jump down here. We are applying LSH. LSH is the same technique that we used before. We will show some other techniques here in just a second, but we wanted to highlight that LSH is not unique to the collaborative filtering stuff that we did before. We're applying it here to our titles. We're putting our titles into buckets of likely similar type titles, but let's take a look at the recommendations we're getting. So Ian, we're going to pull up that coaster here. It's got this really gosh awful ID. I'm not going to try to spell out for folks, but there's our coaster. It's title and a lemata. We can take a look at the other scores. We are going to calculate our similarities and then use our similarity to then rank these things. Here are results. What are you seeing here?
So as you can see, the result is not too bad. They seem quite reasonable and are all some kind of beverage coasters. And do remember that we just use a very simple and straightforward technique here. And since titles are short, they just have a few words, meaning they carry less information. But I think our recommendations are related to our candidate beverage coaster.
Yeah, and if I had to take a look at this, I would say that this is pretty reasonable. But you know what? I want a hard metric. Where's my hard evaluation score here?
So unlike a collaborative filtering for content-based recommendation, there's no ground truth for you to evaluate your result. And there's a lot of subjectivity in it. All you can do is look at the results like what we just did to see whether they make sense to you. And it would be more powerful if you could define your goal for the recommender and do online A/B testing to see if it is really helping your goal.
Yeah, and that's something we came up with against quite frequently when we were going through the recommender literature. There's a lot of what we call offline metrics, like we looked at before, where you can use it to make sure that you're not, kind of misaligned with your goals. But the ultimate test of any recommender is to get it in front of your users and to collect information on their interactions. And so what a lot of folks do is they'll actually put it out there as a small pilot. We might call it an experiment, but basically it's a small pilot where some random subset of users actually are exposed to this. And we look at how they engage with it relative to folks using an alternative mechanism. And then we pick the winner and then roll that out to the rest of the population. That's our online evaluation part of this. Again, A/B experimentation is kind of what we describe that at in the literature, but fundamentally is we don't know until we really get out there with these kind of things. And so that's going to be an important part of any recommender development strategy. So Ian, let's take a look then at descriptions, because to me, I'm a little concerned that we're basing this on title, and it looks like we actually got some good results, but I'm thinking descriptions might carry a little bit more information for us. So talk to us about how we're going to approach that problem.
Yeah, as you can see, descriptions are much longer than our titles, which means we have more data to process and more complexity to deal with. So a straightforward word count like TF-IDF may not be economically viable. So we need to find a way to first reduce its dimension and focus on just the core concept of these words.
Okay, so I see here you're doing some basic tokenization. So you're splitting the words out like you did before. Let's talk about then some of these techniques we might use to turn this into more of those topics or concepts.
Yes, so here we use a technique called LDA, which is simply looking for combination of words that appear frequently together, an idea of a word cluster. And the clusters represent different topics. And the LDA is used to see how different topics contribute to different descriptions using numeric scores.
Okay, so LDA is going to take our words, it's going to look at words that tend to occur together frequently. It's going to come up with, an easy way to think about it, you described it as a cluster. In the formal literature around LDA, it'll describe it as a topic. there's basically groups of words that tend to occur together, and then we're going to score a given description on the topic's contribution to its structure. I think what's interesting on this, when we're going through the literature, there are a lot of examples that try to explain the notion of a topic in terms of human relatable kind of concepts. When you actually start looking at this across a large corpus of data, the clusters don't always align with our human notions of what we would consider a topic, because again, it just really represent clusters of co-occurrence. But okay, so you come into here, to get the LDA working, looks like you're applying the limmatization techniques we saw before, so you're cleaning up the words and moving them to standard forms. I notice you are doing some word counts, but you're doing this with the hashing TF, not the count vectorizer. So talk to us a little bit about that.
So here we implement the hashing TF as a shortcut to speed up the process because descriptions are much longer. But the basic idea is still counting as the counter vectorized.
Okay, so we're getting these scores. If I scroll down here, I think I can see the scores that come in. They look an awful lot like what we saw before with our titles. But what's interesting with this, again, is we're using a shortcut. And what's really important about this shortcut, when we did the count vectorizer, it actually went through and got the unique words and then went through and counted the occurrence of each of those words. So every word was given a spot to be considered. Here, we're using a trick where we actually hash the word to come up with an integer value. And then we just count the occurrence of those hashes across here. Because we're doing a hash, there is the possibility of a collision that can occur here. But that's one of the trade-offs. We're actually trading accuracy for performance. When we tried to actually use the count vectorizer with this data set, and you see these descriptions, they're long, but they're not like overwhelmingly long. But still, it took a considerable amount of time to get through that. Whereas I believe with the hashing TF, we were doing this in seconds. But we're still not at the LDA. So here we go to the LDA. It looks like you're specifying the number of K. It's interesting, same term we'd use for like K-means testing, but you're specifying the number of topics or clusters that we want to generate here, some number of iterations, and you have it go through it. When I look at the results, you said here you wanted 100 of these. And we typically found in the literature, most people for this type of stuff were doing between 100 and 300. So there is something you want to play with here to get your stuff. Here are the different topic contributions to our descriptions. Okay, so I have numerical values, a little bit different from what we had before, but conceptually where we go from here would be about the same to make our recommendations. All right, so that's the LDA technique. We normalize these as before, but let's talk about a different technique. What is word2vec and why might I want to use this as an alternative?
Yeah, so as for now, all we did is count the frequency of words in order to determine similarities. And next we could take context into consideration, like by looking at the sequencing of words appear in a description, we can use word2vec to get concept within descriptions. This is a slightly different approach compared to LDA, but in the end, they serve the same purpose.
Okay, so it's a slight variation on what we did before. The underlying technique is different, and we may get better results or just different results than what we have with LDA. But fundamentally, you're reducing the complexity of this, right? You're taking it back down again to 100 of these word clusters or associations we're referring to as concepts here. Here's the implementation. Again, we're taking it down to that same 100, and we are getting our scores from there. Okay, fairly simple, straightforward. So I have two techniques that I could apply here to reduce my descriptions down to something manageable. From here, it looks like we're calculating similarities very much the same way we did before, except to put things into buckets, right, to manage the number of different descriptions I have to compare, I'm not using LSH. What am I using here? Terry, is this you?
Yes, Frank Brian. So we use LHH for title to find similar item last time. Here's another technique, what we call K-means clustering. So using K-means clustering, we can assign the product to cluster based on the feature similarity. And we can then use cluster assignment to limit our searches for similar product that found within one cluster. Pretty similar idea with LSH. So in the Q&A session, there's question asking, is the LSH similar to the clustering technique like K-means? The short answer is yes. LSH will be fine here as well.
Okay, so in all of these, whether we're using k-means, or in this case, we're actually using bisecting k-means, which is a variant on that. If we're using other clustering techniques or we're using LSH, fundamentally what we're trying to do is to subset our data and to say that we believe that these descriptions or these users or these products are more likely to be similar to each other than folks that would be associated with other clusters or other buckets. However you get there, that's up to you and what's going to work with your data. Computationally, we noticed that LSH did work a lot faster than what we're seeing here, but this is certainly more familiar to a lot of folks. And so if we're achieving the same goal, choose which is going to work best for you. So we do that. We can actually see the buckets here. Here's the distribution of our individual products across these different buckets. It's not perfectly even, and we never really would expect it to be, right? We would always expect certain more popular clusters than others, but any given bucket is no more than 400,000 different products that we have to consider. That's very manageable on a system like this. All right, so we come in here and we're going to calculate distance. Now, when we were using LSH, LSH had built-in Euclidean distance calculations. We don't have that here. One of the challenges that we came up against, and we had to fight through at the beginning until we figured this out, was that you can't pass a vector via Python into a pandas UDF. So if you'll notice throughout some of the earlier stuff, we used quite a number of pandas UDFs to write Python-based user-defined functions to calculate things for us. We could decompose our vectors into the underlying indices and values and pass those around and reconstruct them inside the functions, but that was really slow. So the trick we used here, we took advantage of Scala, which can receive the vectors in their native form, and we registered a user-defined function written in Scala and registered it with the SQL engine. That allows us, when we get down to here, I'm going to jump ahead just a little bit to show this, but that allows us right in here to call a SQL expression as part of our logic. And we're doing this using Python, but to call that Scala function, pass the vectors right in and do the calculation. If I had wanted to not use Euclidean distance, if I wanted Pearson's R or cosine similarity or some other distance or similarity calculation, we could easily take these vectors and do the logic over there and just pass it over the same as we did before. But let's get reoriented to this. Here is our coaster that we've been picking on throughout this thing, broken down into the words in the description. We have scored it using, looks like we're using word to vec here that's been normalized. We do our weighted averages calculations here, or sorry, our similarity calculations, not a weighted average, and we're getting some results. So Terry, give me your thoughts on what you're seeing here.
Yeah, so the first item is basically the sample data there itself, and where the similarity score is 1. The second one, the similarity is 0.76, and it's pretty high too. And if you compare the description carefully, most of them is quite similar actually, and that makes sense why this item is at the top. But if you go to the 6th item, where you see the similarity score is significantly dropped up under the 50%. And if you look at the description, it looks like it's actually recommending another item, which is Merck. And that is kind of weird, right, Brian?
I would say so, right? I came here for coasters because I got in trouble for putting glass on the furniture, and you're actually suggesting more glasses. I think we're going the wrong direction with these descriptions. But if I look at this, there seems to be a reason why this might be popping up. If I look towards the end of it on this, it looks like it references another product, which is a coaster gift set. And so this kind of leads us to a thought about how we want to handle large verbose text like this. I mean, Terry, what did we come to in terms of conclusion on that?
Yeah, so the reality is that the description is really long, right? And I mean, what manufacturer would do is they would like related this item with the other products. Like for example, if I purchase a bottle of milk, and the description of that milk is probably saying the milk is good to use with cereal. And then when you recommend, when the sample product is cereal, that milk description probably comes out. So it's kind of makes sense why the mug comes in right here. So here's how I might deal with this. So normally, the further up of the description you go, the more likely you will get the core concept inside of the description, right? So what you can say is, hey, word to web, only look at the first 500 words. And we did limit the first 1,000 words, but seems like we need to make the number smaller. And if we do that, the frames at the end of the description, like the coaster, probably drop out, and the recommendation list probably maybe better.
Yeah, so the Word Vec actually has a setting for this that you can control how many words you want to consider at the top of it. And we'd expect in most descriptions that the most meaningful concepts are going to be conveyed right at the top, right? If I'm buying a toy and at the very end it says, don't forget to pick up batteries, right? I don't necessarily want that toy to pop up anytime I'm looking for a particular type of battery. So we probably want to focus on the beginning. So we left it at the default of 1,000, and we explicitly put it here so people could see that. That's something you could adjust. The LDA doesn't have that same notion because we're not looking at words in a sequence. But if we wanted to do something similar there, what we could do is we could truncate each of our descriptions up to some maximum number of words and then apply the LDA transformations to it to get the similar effect. Okay, that makes a lot of sense. So thanks, Terry. I'm going to highlight one other item that we used here just because we explored this. And it's really impactful, but it got a little weird and we had to go down a creative path. And I thought maybe this would be helpful to some folks. Again, all this is going to be downloadable, so you can bring this into your environment, kick the tires on these. We're still working with the same type of recommender though, where I'm trying to relate similar products. And as you saw when we did the description-based stuff, we got a lot of things that were technically outside of, say, like a product category. And that might make for bad recommendations in some scenarios. In others, it may be actually what we want. But what might be nice to do is to take our product category information and use that as the basis for constraining what we're seeing here. So let's take a look at our categories. So if we take a look at our categories, you can see that they're broken down as an array. Here's 3, some of these are longer, some are shorter and whatnot. Here's some arts and crafts stuff, and there you go. So what I'd like to do is take a look at different products and compare the similarities between their category assignments. Now, each category level has its own unique name. And there's no reason that level 2 in this one might not overlap with level 2. Like we could imagine there are books on floral arrangement, where the top level is books, but the bottom one is floral arranging. Here we're looking at arts and crafts, and the bottom one's floral arranging. I need to make sure that I'm not colliding or saying that this floral arranging is similar to the book in this scenario. And others, I might want to do that. So what we're going to do is we're going to write a little function that's going to clean up these categories and append the parent level stuff to it. And so you can see here, each level is preserved, but we tack on its lineage into the name. And then from there, we're simply going to do a one-hot encoding of these categories. To do the one-hot encoding, we're actually going to use a shortcut again. We're going to go back and use either the count vectorizer or the hashing TF. We used that when we did the TF-IDF scores, and we did that as a data prep stage, our step for LDA. What we're going to do here is we really just want to count the occurrence of the word. Does it occur inside this structure? And so we're going to flip on this argument to binary equals true, and it gives us the equivalent of a one-hot encoding for this kind of a data set, which is what you're seeing here. Then from there, we calculate similarity. We'll get into this a little bit more later, but in terms of similarity, we can't calculate similarity in terms of Euclidean distance or cosine similarity or things like that. We have to use a different type of similarity. So this is called Jaccard similarity. We're simply going to say between two different products, what portions overlap relative to the overall portions between the two. A very, very simple calculation. We're going to implement that just as we did before using Scala. So here's the Scala function implementing Jaccard similarity. And if you had other metrics, I mean, obviously you could plug your own functions in there. And then we're going to do our calculation. We're going to again pull up our coaster. and we're going to find other products that are inside the same category. Now, what you can see here is there are a lot of things that fall under the coasters category. We were kind of surprised there was actually a coasters category inside of here, but there it is. But look at the similarity. They all come down to 1, and if we scroll down far enough, we'll start getting some 0.5s, some 0.25s, and things like that for things that are a little bit outside but still related to our products. This alone would be a poor basis for making a recommendation. But what we could do is we could take a recommendation off of categories and multiply it against the similarity scores coming off of descriptions or titles to then have an adjusted recommendation that we then use to then determine what to put in front of folks. There's a lot of creativity again in how you can bring together these different things. We can use titles in combinations with descriptions, in combinations with this categorical stuff, in combinations with price and manufacturer and tons of other features that are inside this metadata set and bring them together. There's some interesting books that talk about how to do this, and we have a discussion about it down here. But hopefully most people can kind of make that leap to where we go from there. There's one last thing I'm going to highlight before I turn it over and we go back into questions. We said before we couldn't do evaluation metrics on these things because we didn't have base truth. We do have user ratings though. This is a scenario where people are rating products on scales of 1 to 5 stars. And so what we're working on, and we are not complete with this yet, so I won't go through all the code on it, or really any of the code on it, just want to show you that it is in the works. We're going to go back and we're going to construct user profiles where we actually go back and take historical ratings that people have applied to these products and use that then to weight some of the same features here. So now we'll have not just product recommendations, but user-aligned, personalized product recommendations coming out of here that could be used as a slight alternative to what you saw before when we did the collaborative filtering. So that's in the works, and that'll be there here in about a week or so when we publish these things out there. So with that, let me just highlight one other thing. So you heard a lot of voices that were in here as we were doing this presentation. We had Balaji at the top, followed by Yi, and then Yin and Terry. These guys have really poured their hearts and souls into this work. Again, we have 11 notebooks worth of content that we're going to make available to all you guys shortly after this presentation. But I want to thank all these guys for the tremendous amount of work and the sticking with itness that they've put into this. We've had to chase a lot of dead ends and a lot of confusing literature to figure this stuff out. And there's so much here that I think is going to be helpful to you guys. So I would encourage you, if you're on LinkedIn, reach out to these guys, tell them thank you. That kind of acknowledgement is really big as you're getting started in this space. And again, they've done an outstanding job, and I just couldn't be prouder with what they've done here. So with that, I'll tell you what, how about we turn it back over and take a look at some questions. Steve, do we have some questions come up?
We do indeed. We have first question here is why rely on only one most lookalike? Why not pick 15 or 100 lookalikes to pool in a next best recommendation?
Okay, so there are decisions that you have to make in here throughout here. One of the big ones that we made, I don't know if folks noticed it. Let's go back here where we're looking at similar users on the collaborative filter. Here we go. So we talked about using LSH to put people into buckets, and then we picked 5 or 10 or however many. One of the things you'll notice too is that when we did these, we included the item, the user or the item itself. So we said that this user is most similar to him or herself and needs to be included in these weighted scores. We did the same thing on products. These choices, I wouldn't describe them as arbitrary, but they're informed based on kind of common practices and an understanding of your users, your scenario, your data. In this one with groceries, because again, people tend to buy a lot of what they have bought in the past, including that user inside the recommendations made a lot of sense, and not straying too far made a lot of sense. In other scenarios though, if my goal was not to help this person maybe get to the checkout faster, but was instead to introduce new and novel things, I would certainly want to look further than what we did here And I probably wouldn't want to consider my past purchases other than as a means to find similar users or content to put in front of folks. But it's a decision that you make. It goes back to the art of this stuff.
Awesome. Another question, this one from Soham Bhatt. Is LHS similar to clustering techniques like k-means?
Yeah, Balaji or you guys want to jump in on that? And you are just jumping in all on mute, so I will take it from here. So the reality is, in terms of the way it actually works, the answer is no. Under the covers, it actually is doing something a little bit different. But in terms of what it's giving you, right, the reason we're doing it, it drives you to a similar outcome. It's simply a means to constrain the number of comparisons you're going to have to do. If I can figure out who is more likely to be similar than others, then I can limit my similarity comparisons to just those that are hovering around a cluster, centroid, or sit inside of an LSH bucket. But it's just a means to put people into groups. All right, Steve, what do we have next?
Awesome. We got a few more here. Have you compared the results of LSH to brute force groupings?
We did. We put a lot of time into this. So let's see. Let's go back to this notebook, and we skimmed over it because, again, 11 notebooks. It's a lot for anyone to absorb. But inside of here, we actually do an exploration of what the brute force looks like. And so we're going to take you through a brute force. Now, that said, we're going to grab a small subset of data. One of the things we want to show you is how on a fixed size cluster, and I'll find it in here somewhere, how the processing times tend to grow as the number of users you consider grows. And you can quickly see how this gets out of hand on a reasonable size cluster. I want to emphasize there's no problem with doing 40 billion comparisons. You can totally do that work. It's just going to cost you a lot of money to do it. And a lot of our folks would like to find a shortcut that gives them good results without having to spend that much money to get it. And that's where LSH comes in. But what we did with LSH when it came time to evaluate, and we did it in a couple places. Let's see if I can find the one in here. I think we have to get past this next visual. My apologies, guys. There's a lot of code that we put together to explore this. We felt like it was a really underserved technique. We actually came into here and did the brute force, we call it the exhaustive similarities in here. And we then lined it up for a given user with LSH with different settings. And then what you can do is, here's our brute force. So this AB is truth. These are the actual similarities. And here's the actual distance between it. And then you can see with the different settings we have here, how LSH finds those most similar. It always finds the user that we use as our sample user, that's user 148, but it takes a few tables to come in before we start filling in the gaps here towards the top. Again, this isn't, you really need to be careful about how you look at this stuff. What we're seeing here is an artifact of two different settings, not just the hash tables. We kind of skimmed over how you configure the number of buckets you put people into, and that's very important. So how you vary these settings will determine how soon people will start to show up in here, but also the number of computations you're going to end up with. And so we show a lot of, once you do LSH, how you actually can then go back and determine the number of comparisons you're now putting on your plate relative to the gains that you're getting here. But yes, we exhaustively go into that.
Awesome. We have a few more questions here. And by the way, folks, in case you have questions, feel free to add them into the Q&A panel. Our experts here are ready, willing, and happy to answer anything. Next question comes from Joseph Stoy. Are distance and similarities built only on behavior, or are you always using descriptors?
Are these always based on behavior? Honestly, this is a place where you can get creative, and there are some hybrid methods that we have not explored here that kind of bring the two together. To be honest, once you get comfortable with the core concepts of similarities, I think you'll start to see you can get really creative in terms of how you approach that. So first of all, what your metrics are, but also how you can combine it. So I could imagine a scenario where I might come in here and based off of user similarity, make a set of recommendations but then use product similarities to maybe adjust the sequencing of things. And it may be through simple multiplication, it may be through kind of weighting different recommenders and combining the results to get a combined score. There's a bunch of different strategies here. The key thing that we kind of go back over and over again, and again, there's a great white paper that we reference in one of these notebooks when it comes to evaluations, is to really carefully consider how you're looking to use this recommender. Steve, you made the point in your presentation that you really need to think about this as a journey. And at different stages of the journey, you really have, your users have different goals, and you as the retailer or the manufacturer selling them these goods have your own goals. And those things will determine how you want to approach these problems. The key thing is to understand, again, things like normalization and how to overcome some of the scaling problems you have in approaching these, and then really the sky's the limit. Get creative.
Awesome. We have a few more questions here. And again, folks, feel free to add questions into the Q&A panel here. This one from Naga. Since I joined a little late, didn't get the answer for sources used for the session. Would be great if you could share with us the DBC file.
Yep, we are going to make all 11 of these available. It'll probably be right after Thanksgiving. If somebody has an urgent need, hey, I'm doing this right now and I want to work with you guys to get them, we can make early copies of this available. Just understand that we will not have done all the Q&A on every last aspect of this that we like to do. And some things may be a little partial towards the end, like the one thing I showed there towards the end. But we can do that. If you want to, I don't know if we can throw up my email address and just let people email me on that. Be happy to take those requests. I'll just put this here real quick.
Awesome.
Okay. So shoot me that note and we'll get with you. But otherwise, we will be sending a note out where you can grab all these. In terms of the data sets that we used, for the user, for the collaborative filters, whether it was user or the item-to-item based collaborative filters, we use the Instacart data set. The Instacart data set has 3 million transactions related to grocery purchases by about 200,000 customers against 50,000 products. I really like that one because while I think that the number of transactions and number of users is probably pretty low for a typical grocery store, a good small to mid-sized grocery store will typically have about 25 to 50,000 items within it. So it's fairly representative of what you might see there. Now, some of the bigger guys will have 100 to 200,000 SKUs what's inside their stores, but still, I think that you could extrapolate what we've done there very easily to something a bit larger. And so it's very, very, I think it's a very good quality data set to explore. For the content-based, we used the 2018 Amazon data set. We did limit it to those that products and users which had 5 ratings associated with them. There's another data set that's a little bit more broad and doesn't include the rating information. But we felt that that would give us some options in exploring both content-based as well as ratings integrated content-based recommendations. And so that's the secondary data set. These are all publicly available data sets, so we have the links to them so that you can download those, bring them to your environment and run these notebooks. And then ideally, once you've got oriented to it, start making adjustments and playing with some of these things that we've been talking about.
Awesome. Another question from Naga. Are you using NLTK? I believe NLTK development is stopped as they've heard from Microsoft.
It may be. To be honest, we are using NLTK. There's no reason you have to limit yourself to that. It was just, it seems to be the most popular right now. And so we went down that path. So yes, we are using NLTK, but you can install any number of different libraries in here. Now with NLTK, you do have to download a corpus, and you also have to have a part of speech predictor. So our corpus is WordNet, and our part of speech predictor is this average perceptron tagger that's inside of here. With this, you can't just easily install this via code. There is a way to do it, but there's some overhead that comes with it. And so we found the most reliable way to deal with this was actually to write an init script, which you're seeing here, and then associate that script with your cluster. That was the best way to approach it, but we did explore a couple of different paths. So NLTK is pre-installed on the Databricks ML runtimes. but you do have a few additional things to put in there, and we'll show you how to do that. If you find another library that you think works better, then by all means, bring it into the environment. That's one of the great things about Databricks is it's super, super flexible and focused on bringing on board open source technologies. So if you're stuck on that, if you're having a problem getting something working in there, again, give us a holler. I'll put my stuff back up here and recognizing what I'm signing up for by showing my email address here, but still hit me up and we'll work with you to see what we can figure out if you're having some difficulties.
Brian always going the extra mile.
We do have more for the team.
Yeah, we do have time for more questions. Again, if you have questions, drop them into the Q&A panel here. 2 more questions right now. One from Francois. How did you choose the number of clusters, k-means, and number of topics LDA?
Yeah, you know, we honestly, when we're dealing with some pretty sizable issues here, and so the best way to do it is to use the elbow technique. If you're familiar with k-means, this is the way you basically look at like a silhouette metric or something like that, kind of hitting an inflection point to know kind of the sweet spot for your data. We did not do that here. You know, with this one, it's a bit of a balancing act. You want to have good metrics that reliably pull things closer to those clusters. So when you say that these things are more similar than things outside those clusters, that the metrics telling you that, yeah, you can rely on that. Here's a quantification of it. At the same time, you don't want so few clusters that everybody kind of falls inside the same buckets. You want to spread this out a little bit. So this is an odd situation where you're going to use k-means a little bit differently than what you did before, with a heavy emphasis on spreading the data out, recognizing that you're injecting some inaccuracies into your later calculations, but you're trading off accuracy for performance. And that's something you're going to come back to over and over again. You'll see it with LSH, you'll see it with how k-means is applied, you will see it with really any number of different approaches where you have to find that right balance for your scenario. Remember, when we're dealing with content-based predictors, where we use that technique, when new products come in, I need to get those guys processed and added to the mix. If I incorporate ratings, whenever new ratings come in, I need to come back and reprocess chunks of this stuff. When I'm using user-based similarities or item-based similarities, anytime there's a purchase, I may have to go back and revisit these things. Ideally, that's happening with high frequency. And so to keep my recommendations fresh, I need to be able to go back and reprocess these matrices really, really quick. And so performance becomes really critical for me hitting my goals. And so we start having a conversation about how fast do you want it and what are you willing to give up to get it?
And we have one final question. Again, folks, we do have time for more questions. If you have them, feel free to drop them into the Q&A panel here. The one question we have left is from Rita. Have you looked into matrix factorization for predictions? If so, how do results compare to approaches you demonstrated?
Thank you for that. So Rita, we made the conscious decision after a little bit of initial exploration that we wanted to focus on what are called the memory-based techniques, where we actually use the explicit information provided by our users or the implied rating provided by our users to calculate these similarity matrices. There are higher form type recommenders that are out there. ALS frequently comes up. People are using deep neural networks today. Matrix factorization comes in as well. There's a whole bunch of techniques that you can start bringing into this that I think do a really good job of things. But the problem we kept running into was with those, it seemed like a lot of folks were throwing technique at the data to get a result. And by not working at the ground level up, you started losing insight into places where you could start making adjustments. And so again, our focus really was on education and kind of getting started from the ground up. And so we focus on the memory-based techniques to fully expose the different ways that you can start playing with how you approach this problem. Having done this now, I want to go back and take a look at these higher level ones. But I'm glad we didn't start there, in that I think that we would have missed a lot of the subtlety that's inside of here and the opportunities for crafting something that can better align with a particular set of needs that we might have. But yeah, I think that you'll see more content from us over this next year, and we definitely want to go back and explore those things.
Awesome. So with that, we've captured all of the questions again. If anyone in the last couple of minutes here has any questions that they want to have covered, absolutely feel free to put them into the Q&A panel here. But just to reiterate what Brian shared, we'll make all of this material available after the call. We'll send out the notebooks that we have, and all of these will, as with most of our, or actually, as with all of our other notebooks related to the types of solutions that we're building, the solution accelerators we're building, they are all available at databricks.com/blog in case you're looking for exploring other notebooks that we have available. So I'm not seeing any other questions here. Brian, any final words of wisdom before we wrap up here?
No, just want to thank everybody, and again, thank our interns for their efforts here. Our sincere hope is that if this is something that you're pursuing, that the content we put together helps you get started. And again, we'd love it if you'd reach out to our guys and tell them thank you, maybe share some of your stories with them. That'd be very much appreciated. So thank you, everybody.
Thanks again for joining us, and we hope to see you on our next event. Thanks again.
Thanks, guys. Thank you, Brian.
Thank you.
Thank you, Steve and Brian.
Are we off the air, Steve?